Okay, so what's standing in your way to applying the fundamental theorem of calculus part 1?
There's not a constant at the bottom.
Yeah, so you need to flip it over. F of x is the opposite tan to x of tan theta d theta. So what is f prime of x going to be? Negative. Nope.
Oh no.
Done.
But it's not continuous.
What?
But tangent is not continuous from x
I
from
got it.
thing at 10.
Ah, so is there a continuity problem here?
Yeah.
Do you have any idea what x is?
No.
So therefore, how can you say it's not continuous?
How do you say it?
Touche. Touche. I don't think you have to worry about it in this case. I don't think you have to worry about it in this case because you don't know what x is. So how about this? Assume the case that makes it easier for you.
Okay.
Like, I understand what you're saying. If you pick some arbitrary value, it wouldn't be continuous. There are ways mathematicians kind of get around that, where they say things like, for example, is tangent continuous everywhere? No. Is it continuous on its domain?
Yes.
Yeah. So you could say like x is any value that's in the domain of tangent theta, right? And then you eliminate that problem. They're not. You make a lot of assumptions like this whenever you do any math problem. You know, all those questions where it's like you're traveling on a road or you're in a river. Like, well, the water flow in a river isn't the same everywhere in the river, right? The closer you are to the shore, there's more resistance. So the river flow is slower closer to the shore. There's traffic issues. So like a lightning bolt could strike. It's like it's the Calvin and Hobbes approach to math. Like anything can happen, right? Have you seen those math comics with Calvin and Hobbes? He's like, Hobbes, tell me, how do you do 3 + 6, right? Okay, so for this one, can you apply the fundamental theorem of calculus?
Yes. Yeah.
Okay, so g prime of x is equal to ln x, and then you're done. The definite integral. So how do we rewrite that so it's a little nicer? Yeah, so you have -5 to 5 of 2x to the -3 dx. Okay, this is a fun one. I see what's going to happen here. So you might want you try doing this, right?
Yeah.
So you integrate it. So it's going to be x to what power?
-2.
-2. You're dropping it to the front. You need to make it a 2. So what do you plug out front?
1/2.
Nope.
Or,
You want 2 to be there, right?
oh. -1.
-1, right? To the
It turns it.
you drop it down, it becomes positive. And what do you value it from and to? -5 to 5. Okay. Nice. I'm okay with this. So what do you end up with? You have -5 squared minus -5 squared. A super easy way to mess these up is to mess up the negative signs. Do you understand what I'm saying, everybody?
Isn't it to the negative?
Oh, to the -2. Thank you. Yes, to the negative. See, look at that. I already messed it up. But do you see where all that plugged in? You have to subtract the 2 because you're using fundamental theorem of calculus part 2. You're evaluating the integral at the upper limit, and then you're subtracting the integral evaluated at the lower limit. So you plug the 5 right there, the -5 goes right there, right? But that negative sign goes both places, and then you have to subtract the 2. So is it really easy to mess this up?
Yes.
Yeah, it is. So what do you end up with? -1/25, and then it's minus a negative.
Minus.
So what is it going to be?
+1, 0.
Isn't it?
Plus, oh no, because this is positive, right? And then these cancel out right there. They cancel, right? So what do you end up with? Does that make any sense whatsoever? You sure?
No.
Well, the book
because-
said it was wrong,
No, because it's
so-
going.
What did the book? Okay, so you did look this up. What did the book say?
I don't know what the
It
book
said
said.
it didn't exist.
Ah, it didn't exist, and that is totally true. So you might look at a picture of this and get a better idea. You are integrating across a what? What does that? What do you say? You're integrating across an asymptote. When you attempt to integrate across an asymptote, you're integrating across a discontinuity. Fundamental theorem of calculus part 2 only applies for sure when you are integrating on a continuous function. Is 2/x³ continuous at 0?
No.
No, there's an asymptote. This right here, not, so I'm circling too big there. This right here is not continuous on -5 to 5, right? Because of what value? 0. So what does that mean? So FTC number 2 does not apply. It kind of almost makes sense when you look at the picture because it looks like it's the same thing above and below. Do you understand what I mean? Like an argument can be made that it might work, but we're not doing that right now in this class. The point is you can't use the fundamental theorem of calculus on this because it's not continuous across the interval you are integrating across. Y prime. So we're going to use y prime. We're going to find it using the first part of the fundamental theorem of calculus. So this is pretty nice because this is just x. So what is the first derivative? 1 plus t squared to the what power?
-1.
I'm just writing it like that because it's easier to differentiate now. Do you agree that that's the first derivative of y?
Yeah.
Cooper?
Yeah.
Okay, so if that's the first derivative, x. Sure. Yeah, absolutely. That is good for total properness. Okay, so now we take the derivative using the chain rule. So y double prime is going to be what? Negative 1 plus x squared times, oh, to the what power? Mm-hmm. Yeah, exactly. What does that simplify to? Negative 1 plus 2x over 1 plus x plus squared. And we're interested, we want to know when that is what? We want to know when it's positive, right? And you're getting to my next question, which is what are you really looking for now? Where it's 0, and then you test the intervals. What's the only way to make a fraction equal 0? The numerator, right? And you don't care if it's negative 0, right? So it's 1 plus 2x has to be 0, so x has to be negative a half. So now you have this negative a half right here, and you have the x value, and you have y double prime. Well, what's the second derivative when x is negative a half? 0. We know that it's 0 there. Is it 0 anywhere else? No, there would be other solutions to this if there were other places where it crossed the x-axis, but it doesn't. So you know this is the only place. So what does that say about each side of 0? Has to be all positive or all negative on each side. Because if it was positive and negative, there would have to be another or discontinuity. But here's the thing, is there a discontinuity here? No, because is there anything you can't plug in here? No, because is there any way to make the denominator 0? No. This is always positive, and then this 1 plus x squared, does that ever cross the x-axis?
No.
How do you figure that out for sure?
Because x squared is bigger than x.
Not always. What about a fraction?
No.
Well, look. X squared is always bigger than x, except where x is between 0 and 1, right?
Yeah.
But there's a 1 here, right?
Yeah.
So look, this right here, like if it's less than 1, you know, it can't be negative, right? So if it's like negative a half, you can't get rid of that 1.
Yeah.
You also tested the discriminant, negative b plus or minus, b squared minus 4ac. If you try to use the quadratic on this, what kind of answer would you get?
Not imaginary.
An imaginary. You get because it does not cross the x-axis, right? So you check now. You have to check values on either side. You have to check values on either side. So what's an easy value on the right of 0?
1.
What's easier than that?
0.
How do you plug in 0, right? It's going to be 1 on the bottom and negative 1 on top. So what is it going to be? Negative. Now, are we guaranteed this to be positive that this is negative?
No.
No. Can it go negative 0 negative?
No.
Absolutely.
Yeah,
Oh,
sure.
yeah, you can. The point is you have to test both sides.
Yeah.
So what's to the left of negative a half?
-1.
Negative 1, right? Plug in negative 1. Well, this is always positive, right? Squared. Plug in negative 1. 1 minus 2 is negative 1. Negative 1 is positive, or positive is? Positive. So where is this concave up?
Less than
0.
Yep.
less than -1/2.
Oh, negative 1/2. Thank you. Correct. There you go. So it's concave up.
What was the first part to that? I missed what you said.
So how many of you started off in the land of integrals looking at something like this? So this is y equals x squared from 0 to 1. And how did you initially estimate that area? Draw a bunch of rectangles, right? You drew first rectangle, you drew a second rectangle, drew a third. Generally speaking, what was easy? It was easier to use. Generally speaking, it was easier to use rectangles that have the same width. Just makes the math a little easier. So how do you make the estimate more accurate? More rectangles. You cut it into more rectangles. So instead of that one, you cut it into the area, right? So theoretically, how many rectangles do you want to break it up into? An infinite number of them, right? Or you want to look at that limit, right? So you're going to have a ton of these, right? You're going to have a last one right here. But how many rectangles are you going to have? An infinite number of them. Okay, so if you're going from 0 to 1, and there's n rectangles here. If there's n rectangles, what's the width of one of them? 1 over n. Do you agree with that? So where is 1 over... If this right here is 0, and this right here is 1, this right here represents... That's x1, and what is x1 equal to? 1 over n. 1 over n. If this right here represents x2, what is that? 2 times 1 over n, which is the same thing as 2 over n, exactly, right? So it's 1 over n, then 2 over n, then 3 over n, then 4 over n. Are we okay with that? How do you find the area of a rectangle? You multiply the base times the height, right? What's the base of each of these going to be? 1 over n. What's the height of each of these? The function evaluated at x sub I, where I goes from what? I is between 1 and n. 1 and n. Because what's the last one going to be? xn. But xn is going to be n over n. What is n over n? 1. So you're starting with x sub 1. What is x sub 1? 1 over n. And then what are you going to? X sub 2, which is going to be 2 over n. Okay, so here's the deal. How many of these rectangles are there? Well, there's n of them, and we're looking as n goes to infinity, right? So this right here, if you add these all together, you end up with a value that's getting infinitely close to the actual area. You're getting infinitely close to the actual area. So that's why you see this phrase right here. The limit as n goes to infinity of the sum of I equals 1 to n of... Does anybody remember what else is there? Anybody look this up last night? The function x sub I times what? Change in x. So how does that translate to what we just wrote up top? What is this? That's the width, right? In our example above, that was 1 over n, right? What does this represent? The height. And how many of them are you adding together? N of them, and n is going to infinity. Right, both are fine. So the point is, this summation, this is just notation for, do it first with x sub 1, and then what do you add to it? X sub 2 times this inside the function, and then x sub 3. So this means, what is this telescope to? This telescopes to f of x sub 1 times delta x plus what? X sub 2 delta x plus all the way up to f sub x sub n times. This is a Riemann sum. You're adding all of these pieces together, and you've attacked this before. You have definitely attacked this before in, I hope, this specific problem right here. How many people have seen some? So if we wanted to evaluate this right here using the limit definition of an integral, we would have to use infinite sums. Raise your hand if you've kind of done this before. Infinite rectangles, adding them together, maybe a little bit. Okay, so look, we're going to do this now. What is the function? X squared. We're using the squared function, and we're going from 0 to 1, so it's I equals 1 to n, and it's going to be 1 over n. So what do we have? We now have the limit as n goes to infinity of 1 over n times 1 over n squared plus what? 2 over n squared plus 3 over n squared all the way up to what? And I'm going to leave it as n over n. I'm not going to write it as 1. It's easier to see the pattern this way. Are we okay so far? Yeah. What's a common factor to all of these terms? 1 over n squared is a common factor. So I end up with the limit as n goes to infinity. And if I factor out 1 over n squared, what do I end up with? 1 over n cubed. So what do I end up with? 1 squared plus 2 squared plus 3 squared all the way up to? This right here is called, well, that's not called, it's just what it is. The sum of what? Sum of squares. How many squares? Well, n squares. There is a formula that tells you quite quickly what the sum of n squares is. Does anybody know what it is? The sum of n squares is equal to n times n plus 1 times 2n plus 1 all over 6. This is magical to me. This is magical to me. I love this in math because you have this completely kind of pure thing. Sum of squares is pretty pure, right? Pretty straightforward. And all of a sudden, this thing equals 6. Like, where does 6 come from? Let's see if we believe it. What happens if n is 3? What's 1 squared? Well, 1 plus 4 is? 5 plus 9 is? 14. Let's plug 3 in. What's 3 times 4? 12. What's 12 times 7?
84. Or no.
2 times 7 is 14.
Yeah.
You
We're
just 12
plugging
over
in 3.
6.
It's 84. Isn't it?
Wow, we're doing really well here. I want to pause this just so you don't get this on. Yeah. Yeah, you have the integral from 0 to 1 of x squared dx, which is equal to 1/3 x cubed from 0 to 1, which is 1/3 minus 0, which is? No, we're integrating. We're integrating. The derivative of 1/3 x cubed is x squared. this is the general antiderivative, if you had plus c there, of that. So is this a little bit quicker?
And
Yes,
this
it is a little bit quicker.
I heard.
So first of all, they already told you at the beginning of this problem that you're finding the area under the curve of a certain function from 0 to 1. So where is the width of all the rectangles? Where's the width? Where's the width written?
In the front.
Yeah, that's the width. That's the 1 over n right there. And then how many terms do you have in here?
And
N of them. So that's a sum from 1 to n. So what are you looking at so far? You're looking at the limit as n goes to infinity of the width 1 over n times the summation of I equals 1 to n of some function x sub I. What's x1 in this case? What's x1?
1 over n.
What's x2?
2 over n.
Exactly, right? What function is being acted upon?
1 over n.
Or is acting upon this?
Square
The square root function. So this is just the square root of x sub I. And then you could put this out here. This is the delta x. But what can you recognize it as? This is just the area under the curve from 0 to 1 of what function?
square root.
So you can recognize this as this. And can you evaluate that rather quickly? Sure. You actually really only want to do it this way because do you have a sum of square roots formula? Not really. You can find one, but we're not going to use it. What this question wants you to do is recognize that this right here is equal to this integral, and for you to evaluate this integral. Can you evaluate this integral? You think so? Yeah, what's it going to evaluate to? What's the general antiderivative? No. 2/3 x to the 3/2 from 0 to 1. There it is. You got to add 1 to the power. So what's that going to be? 2/3. All done. You take the integral, what do you get? X squared e to the x from 0 to what? Not from 0 to 1, yeah. From -1 to what? So you have 0 minus e to the 0 minus -1 squared minus e to the -1, like that. What's e to the 0? -1 minus 1 minus 1 over e. So what do you end up with? -2 plus 1 over e.
Yeah, all I did was the